Welcome to all of you students. Today we will going to discuss about the hazardous detection and resolution. This topic is associated with MSc Computer Science 4th semester paper 3, that is elective subject, Advanced Computer Architecture, unit number 4, Advanced Processor Technology. This has been prepared by me, and I'm Suresh Kumar Thakur, Assistant Professor, Department of Computer Science, Indira Gandhi Government Arts and Commerce College, Vaishalnagar, Bhilai. So let's look to know what is hazard. In a computer architecture, a hazard is a possible problem that can happen in pipeline processor. The possibilities of incorrect computation when a CPU tries to concurrently execute multiple instructions which exhibit data dependence. Hazard a problem with the instructions pipeline in CPU when the next instructions cannot execute in the following clock cycle 1 and can potentially lead to incorrect computation result. In computer architecture, hazard is a potential problem that can happen in pipeline processor. We will have to know what is stalling before going to discuss about the hazard in detail. Hazard in pipeline can make it essential to stall the pipeline. Avoiding a hazard often requires that some instructions in the pipeline be allowed to proceed while others are delayed. As a result, so no new instructions are fetched during the stall. We can understand this stall as a freezing, like freeze some instructions. Some terminologies here we can use in our today's lecture. 5 stages, 1 step per stage. We need IF, instructions fetch from memory, ID, instruction decode and register lead. EX, execute operations or calculate address. MEM, access memory operand. WB, write result back to register. Instructions in a pipeline processor are performed in several stages so that at any given time several instructions are being executed and instructions may not be completed in the desired order. A hazard occurs when 2 or more of these simultaneously instructions conflict. So we are going to discuss about the types of hazards. We are getting the 3 types of hazards in our computer architecture subject: data hazards, structural hazards and control hazards. Data hazards. Data hazard occur when the pipeline changes the order of read or write access to operand, so the order differ from the order seen by sequentially executing instructions on the non-pipelined machine. A major effect of pipeline is to change the relative timing of instructions by overlapping their executions. This introduces data and control hazards. Data hazards occur when the pipeline changes the order of read-write access to the operand. Now let's look at our example. Consider the pipeline executions of the instructions. All the instructions after add, we can see here the add, subtractions, and or and XOR, which is the instructions R1, R2, R3 up to R4, 5, then this R11, 10, these are the register, and this is the cycle. 1 cycle, 2nd cycle, 3rd cycle, 4th, like and cycle. Instructions fetch for first instruction, then decode, then execute, then memory, then write result back. Here we are using the terminologies for this one. All the instructions after add use the result of the add instructions in R1 register 1. There we have the add instructions. Write the value of R1 in the WB stage, the fifth cycle, shown as yellow background, and the subtraction instructions read the value during ID stage, that is called ID sub. Here we can see this problem is called data hazard. In third cycle, the result not written in R1, so sub instructions could not able to get the instructions, could not be able to find the value resides in R1. This problem is called a data hazard. Unless precautions are taken to prevent it, the sub instructions will read the wrong value and try to use it. The AND instructions is also affected by this data hazard. The write of R1 does not complete until the end of cycle 5. Thus, the AND instructions that read register during cycle 4 ID AND, in this stage 4th cycle ID AND, and will receive the wrong result. The OR instructions can be made to operate without incurring a hazard by simple implement technique. The technique is to perform register file read the second half of the cycle and write in the first half, because both WB for add and the ID OR for OR are performed in the one cycle, that is cycle number 5. The write to register file by add will perform in the first half of the cycle, and the read the registration by OR will perform in the second half of the cycle. The XOR instructions operate properly because it register read occur in 6th cycle after the register write by add. So we can understand what is data hazard and how it affect with the result. Hazard is created whenever there is a dependence between instructions and they are close enough that the overlap caused by pipelining would change the order of access to an operand. For example, hazard have all been with register operand, but it is also possible to create a dependence by writing and reading the same memory locations. All the data hazard discussed here involve register within the CPU. By convention, the hazard are named by the ordering in the program that must be preserved by the pipeline, like raw read after write, then WAW write after write, and WAR write after read data hazard. RAW. And let's consider two instructions, instruction J, instructions I. Instruction J instruction J tries to read a source before I instructions write it, so instruction J incorrectly gets the old value. This is the most common type of hazard and the kind that we use forwarding to overcome. We will discuss about the forwarding, what is forwarding in after some time. WAW write after write. Instruction J try to write an operand before it is written by instructions I. The writes end up being performed in the wrong order, leaving the value written by instructions I rather than the value written by instructions J, the destinations. This hazard is present only in pipelines that write in more than one pipe stage or allow instructions to proceed even when a previous instruction is stalled. WAR tries to write destination before it is read by instructions I, so instruction I incorrectly gets the new value. This hazard occurs when there are some instructions that write result early in the instructions pipeline and other instructions that read a source late in the pipeline. Because of the natural structure of pipeline, which typically reads value before it writes result, such hazards are rare. Pipelines for complex instruction set that support auto-increment addressing and requiring operand to be read late in the pipeline could create a write after write hazard. Handling data hazard by forwarding freeze earlier pipeline stage until the data becomes available. It is called interlocks. If data is available somewhere in the data path, provide a bypass to get it to the right stage. Speculate about the hazard solution and kill the instructions later if the speculation is wrong. The problem is solved with a simple hardware technique called forwarding. Forward work as the ALU result from both the execute and memory and MAM or write back result. Pipeline register is always fed back to the ALU input if the forwarding hardware detects that the previous ALU operation has written the register corresponding to a source for the current ALU operation. Control logic select the forwarded result as the ALU input rather than the value read from the register file. The load instruction has a delay or latency that cannot be eliminated by forwarding alone. Instead, we need to add hardware called a pipeline interlock to preserve the correct execution pattern. A pipeline interlock detects a hazard and stall the pipeline until the hazard is cleared. This pipeline interlock introduces a stall or bubble for the stalled instructions increased by the length of the stall. Structural hazard arise from the source conflict. Hardware cannot support all the possible combination of instructions. The structural hazard occurs when a part of the processor's hardware is needed by two or more instructions at the same time. A structural hazard might occur, for instance, if a program were to execute a branch instructions followed by a computations instructions. If some combinations of instructions cannot be accommodated because of a resource conflict, the machine is said to have structural hazard. Common instances of structural hazard arise when some functional unit is not fully pipelined, then a sequence of instructions using that non-pipeline unit cannot process at the rate of 1 per clock cycle. Some resource has not been duplicated enough to allow all combination of instructions in the pipeline execute. A machine has shared a single memory pipeline. Here we just getting that concept through this example. A machine has shared a single memory pipeline for data and instructions. As a result, when instructions contain a data memory reference load, it will conflict with the instruction reference for a later instruction, that is instruction 3. This is a clock number 1, 2, 3, 4, 5, 6, and 7, 8, and this is instructions load instruction 1, instruction 2, instruction 3. To resolve this we sell the pipeline for one clock cycle when a data memory access occurs. The effect of the stall is actually to occupy the resource for that instruction slot. The following tables show how the stall actually implemented. Instruction 1 assumed not to be data memory reference, load or store. Otherwise, instruction 3 cannot start execution for the same reason as above. Here, to simplify the picture, we are fetching and we are putting the stars like bubble, place the bubble over here. That it means कि we are trying to freeze these instructions for one cycle. Then next cycle number 5, instruction 3 start from cycle number 5. So it means कि there is problem with load instruction 3, share common cycle and they are having some problem. So we put the stall and we put the bubble in one cycle. It means कि this cycle instruction 3 get freeze and now instruction 3 start with another cycle. To simplify the picture, it is also commonly shown like this. We can freeze the instruction 3 for one cycle, cycle 4. Introducing stall degrade performance as we saw. Handling the structural hazard. Stall the pipeline for one clock cycle that we have seen already. When the data memory access occurs, a stall is commonly called a pipeline bubble or just bubble, since it floats through the pipeline, taking space but carrying no useful work. Control hazard. Branching hazard is known as control hazard occur when the processor is told to branch. If a certain condition is true, then jump from the one part of the instructions stream to another, not necessarily to the next instruction sequentially. In such a case, the processor cannot tell in advance whether it should process the next instructions when it may still have to move to the 10th instructions. Handling branch hazard. Simplest scheme to handle branch is to freeze the pipeline, holding or detecting any instructions after the branch until the branch destination is known. A high performance and only slightly more complex scheme is to treat every branch as not taken, simply allowing the hardware to continue as if the branch were not executed. The complexity of this scheme arises from having to know when the state might be changed by instructions and how to back out such a change. In simple 5-stage pipeline, this predict non-taken or predict untaken scheme is implemented by continuing to fetch instruction as if the branch were a normal instruction. The pipeline looks as if nothing out the ordinary is happening. If the branch is taken, however, we need to turn the fetch instructions into a no operand and start the fetch at the target address. An alternative scheme is to treat every branch as taken. As soon as the branch is decoded and the target address is computed, we assume the branch to be taken and begin fetching and executing it the target performance of branch scheme. So this is the end of our today's lecture. Thank you very much.